Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The objects at the edge of the solar system that might be pointing to something we can't see yet. If you point a telescope toward the edge of the solar system, it almost feels like things are supposed to end out there. Neptune sits at the frontier like a quiet border guard. Beyond it, the Kuiper belt spreads out a wide zone of icy leftovers, often described as the solar system's forgotten debris field. And many textbooks confidently wrap it up with a simple line: that's basically the end of the solar system. But science has a habit of not respecting neat endings. Never say never, as the saying goes. Back in 2003, something inconvenient happened. At Palomar Observatory in California, a sky survey project was doing something deceptively boring, taking repeated images of the sky and checking what moved. In other words, hunting for pixels that refused to stay still. On November 14, the system flagged an object. Dim, easy to miss. The kind of dot you'd overlook unless you zoomed in several times. At first glance, nothing special. Except it moved, strangely slowly. So slowly that it didn't behave like typical Kuiper belt objects at all. Those already far-away bodies still show noticeable motion over days or weeks. This one barely changed at all on the same timescale. At first, the team assumed it was an error. Astronomers, after all, tend to doubt their instruments before they doubt the universe. But then things got uncomfortable. Michael Brown, Chad Trujillo, and David Rabinowitz began tracking it more carefully. The movement was subtle, but consistent. Too consistent to be noise. It was there, just barely moving. They recalculated the orbit. The first result felt normal enough, probably another Kuiper belt object. Nothing dramatic. Then they recalculated again, and again. Each time, the estimated distance grew. And at some point, the question stopped being which region is it in, and became something much more unsettling. How is it even there? It was too far out for the Kuiper belt, but not quite in the theoretical inner Oort cloud. It sat in a kind of empty gap in the models or region that hadn't really been seriously designed in our mental map of the solar system, like drawing a map and suddenly finding something standing outside the frame. Early on, there was even a classic misclassification: maybe it's just a Kuiper belt object with an unusual orbit. Nothing more. But longer observations killed that idea. The orbit wasn't just wide, it was extreme, highly elongated. And its closest approach to the Sun was still far beyond Neptune's influence. That detail matters a lot, because in solar system dynamics, Neptune is basically the outer traffic controller. If it can reach you gravitationally, it can shape your orbit. If it can't, you're outside the system's main rules. And Sedna simply didn't play along. At that point, the team realized they weren't just looking at another distant object. They were looking at something that didn't fit any known gravitational story. Either something massive and unseen was shaping the outer solar system, or our understanding of how it formed was missing a major chapter. Over the following months, more observations came in from telescopes in Hawaii and Chile. The orbit solution stabilized, and a name emerged: Sedna. Taken from Inuit mythology, a sea goddess cast into the deep cold ocean. It wasn't just poetic. It felt oddly precise. Isolated. Frozen. Out of reach. Exactly what the object seemed to be. Call a spade, as the saying goes, and this name fit better than anything technical ever could. But the real shock came when the final orbit was confirmed. Its orbital period, over 10,000 years. Think about that for a second. One full orbit, and human civilization could go through countless versions of itself. From stone tools to space telescopes, Sedna would barely complete a fraction of its journey. It just keeps moving, while everything else changes around it. And suddenly, the questions become sharper. If this is normal, why is it so extreme? And if it's not normal, why does it exist at all? At this point, the discovery is no longer just about finding a new object. It's about something bigger, a crack in our assumed map of the solar system's edge. And perhaps the most uncomfortable part is this: Sedna isn't the only one. It's just the first one we noticed clearly enough to ask questions, and that usually means one thing: the story is only just beginning. What's fascinating is that the name Sedna almost feels like it existed before the object itself was even discovered. In Inuit mythology, Sedna isn't just a simple goddess. She starts as a human girl, but her story turns into something closer to a tragic family drama. Her father throws her into the freezing ocean, her fingers are injured, and she sinks into the deep sea. And that's not the end. She doesn't die. She transforms into a powerful being living at the bottom of the ocean, controlling all sea creatures. Humans can only hunt successfully if they somehow appease her. In other words, she doesn't live in the ocean, she's trapped in it. So when astronomers officially named the 2004 discovered object Sedna, it felt almost too fitting. Because this object is also trapped not in water, but at the very edge of the solar system, isolated in a place where almost nothing else interacts with it. It's like being forgotten by the system itself. And interestingly, this wasn't just poetic coincidence. Around 2005, the International Astronomical Union started formalizing naming conventions for outer solar system objects. Pluto-like bodies were named after underworld myths, Neptune-related objects used sea deities, and the most distant objects tended to follow themes like isolation, cold, and boundaries. So Sedna isn't really poetry, it's taxonomy in disguise. But here's the side effect: once you name something after a trapped sea goddess, the human brain immediately starts telling stories, even if all you wanted was to describe an orbit. Psychologically, it's simple: we don't process data as data. We process it as narrative. And suddenly, Sedna stops being just object 90,377. It becomes a character, a kind of exiled figure drifting at the edge of the solar system. And that matters, because stories stick. People remember a myth far more easily than a list of distances or decimal-heavy orbital parameters. But physics doesn't care about storytelling. Remove the emotional layer, and Sedna becomes something much colder. Its orbit is one of the most extreme in the solar system. Dynamically, it belongs to a class called detached objects, a very literal name that basically means it has been cut off from the main gravitational system. Its closest approach to the Sun is about 76 astronomical units. For comparison, Neptune is around 30, Pluto about 39, and its farthest point may exceed 800, even close to 1000 depending on the model. So this isn't far away. This is outside the normal gravitational architecture of the planetary system, and that creates a serious problem. Neptune is supposed to be the outer system's gravitational architect. It scatters and reshapes orbits over time, but Sedna never gets close enough for Neptune to touch it, not even remotely. That means its orbit wasn't sculpted by known planets. It likely comes from something earlier, more violent, or completely unknown. At that point, scientists had to face an uncomfortable possibility: either there's an unseen structure in the outer solar system, or our model of how it formed is missing something fundamental. Even worse, Sedna's orbit isn't just distant, it's extremely elongated. A very high eccentricity means it spends most of its time far away, almost frozen in the dark outskirts of the system. Only for a very short period does it swing back inward, closer to the Sun. Which means this: over a 10,000 plus year orbit, humanity only gets a tiny observational window to even notice it. Miss that window, and it effectively disappears again. That makes it incredibly hard to explain with standard planetary formation models. Normally, early solar system evolution smooths orbits over time. Gas disks, planetary migration, everything tends to calm things down. Sedna didn't get the memo. It looks like a leftover from an early, chaotic phase, something preserved rather than reshaped. So it doesn't fit neatly into the Kuiper belt, and it doesn't behave like a typical scattered object either. It sits outside the models. That's why scientists introduced a new idea, a potential inner Oort cloud region. But there's a catch: the Oort cloud itself has never been directly observed. So the logic becomes circular in a strange way. Sedna helps define the region, and the region is used to explain Sedna. And in science, that usually means one thing: we're still missing the key pieces of the puzzle. If you strip Sedna's orbit data away and just imagine the object itself, something strange happens. It stops feeling like a moving part of the solar system. It feels more like a frozen sample, something the universe placed in a deep freezer and forgot about. Its diameter is roughly 1,000 kilometers. And that number matters, because it sits right on the edge of classification, bigger than most small bodies, but not quite large enough to become a full planet. In other words, it doesn't really belong anywhere cleanly. And once you look at its environment, things get even more extreme. The surface temperature is around 12 Kelvin, basically just a few degrees above absolute zero. At that point, cold stops being a feeling. Physics takes over before your senses even get a vote. But the real surprise is its color. Sedna is distinctly red in visible and near-infrared light. That has been confirmed repeatedly since the mid-2000s. Similar reddish tones exist on Pluto and some Kuiper belt objects, but Sedna is on the extreme end of that spectrum. The leading explanation points to something called tholins. Not minerals, not rocks, more like a very slow chemical aftermath. Over billions of years, sunlight and cosmic radiation constantly hit surface ices like methane and nitrogen, breaking them apart and rebuilding them into complex organic compounds. No explosions, no dramatic events, just relentless processing over time. As one scientist once joked, if Pluto was an ice world, Sedna is what happens when ice gets slow-cooked in space. Except the oven is basically near absolute zero. Slow and steady wins the race, as the saying goes, except here, slow is measured in cosmic timescales. Because of its extreme distance from the Sun, Sedna also avoids most of the geological resetting that inner solar system bodies experience. No constant resurfacing, no heavy thermal cycles, no real rebuilding. It's closer to a preserved fragment from the solar system's early days than a modern, evolving world. Which leads to a surprising conclusion: Sedna isn't really a current object in the usual sense. It's more like evidence from the past. And once you see it that way, the question shifts. It's no longer what is it? It becomes, how did it end up there? Since its orbit was confirmed in 2004, scientists have proposed several major explanations. And here's the interesting part: they all try to explain the same mystery, but in completely different ways, and none of them fully works on its own. First is the stellar flyby model. The idea is that the Sun formed in a crowded stellar nursery about 4.5 billion years ago. In that environment, another star could have passed close enough to disturb outer solar system objects and fling them into extreme orbits. Sedna fits that kind of signature surprisingly well. But there's a catch: the conditions have to be almost perfectly tuned. Too close, and the solar system gets disrupted. Too far, and nothing meaningful happens. Right idea, very tight odds. Then there's the cluster environment model. Instead of a single dramatic flyby, this version says the early Sun formed inside an open star cluster. Lots of nearby stars. Constant weak gravitational interactions. Over time, outer orbits get reshuffled into extreme shapes. It's elegant and doesn't require a single rare event. But it's also a bit too flexible. It can explain many things, just not why only a small number of objects actually look like Sedna. Then comes the most famous one, Planet 9. Popularized heavily in the mid-2010s, especially through work by Michael Brown and others, the idea is simple: there may be a massive unseen planet far beyond Neptune, slowly shaping distant orbits over time. Sedna becomes one of the possible indirect clues. It sounds exciting. It sounds neat. But there's a problem: Planet 9 has never been directly observed. So in a strange loop, it is used to explain Sedna, while Sedna is also used to argue that it might exist. A classic case of scientific circular tension. Finally, there's the capture hypothesis. Sedna may not have formed around our Sun at all. It might have come from another star system and been gravitationally captured during a close encounter in the early solar system. This is physically possible. Simulations show it can happen. But it's difficult. Capturing an object without destabilizing its orbit is a delicate balancing act. So most studies treat it as possible, but not stable. And when you step back, the situation becomes oddly symmetrical. 4 models, 4 directions, 1 anomaly. Stellar flyby explains the orbit, but requires rare timing. Cluster dynamics explains the environment, but lacks precision. Planet 9 explains structure, but lacks evidence. Capture explains origin, but struggles with stability. Each one solves part of the puzzle. None of them solves the whole thing. So the discussion shifts. It's no longer which one is correct. It becomes which one is least wrong. And in that uncertainty, Sedna quietly sits at the far edge of the solar system like an unsigned answer sheet. It doesn't confirm anything. It doesn't reject anything. It simply exists. And in science, objects like that are often the most unsettling of all, not because they break the rules, but because they don't yet reveal which rules are missing. Once Sedna was first confirmed, the reaction in astronomy followed a very familiar pattern: shock, then doubt, and finally the urge to go back and check if anything similar was hiding in the data. Because in science, there's a simple rule: one anomaly might be luck, but a group of anomalies usually means something deeper is going on. One swallow doesn't make a summer, as the saying goes. And Sedna just happened to sit right at that turning point. By the mid to late 2000s, with large sky surveys like the Sloan Digital Sky Survey and other outer solar system searches, astronomers started combing through data looking for objects with similar orbital behavior. And they found them. Not many, but enough to matter. These objects are now called sednoids. Examples include 2012 VP-113, announced in 2014, along with a handful of other distant bodies with extremely far perihelions and orbits that stay well beyond Neptune's influence. And they share one striking trait: their orbits look too clean. Not clean in a physical sense, but dynamically clean. They barely interact with Neptune at all. No scattering, no strong gravitational nudges. It's almost as if they were never part of Neptune's system to begin with. And that's where things start to get uncomfortable. Because a single odd object can be dismissed as coincidence. But once you see a second, then a third, statistics start to whisper that something isn't random anymore. A pattern begins to emerge: distant perihelions, extremely far aphelions, non-random orbital tilts, and generally high eccentricities. Put together, it starts to look less like chaos and more like structure. But nature usually doesn't do neat. It prefers mess. So when the data looks too consistent, scientists don't celebrate first. They get cautious. The first question is always, are we being fooled by observation bias? Which leads to a second, more uncomfortable idea: maybe we're only seeing what's easiest to see. Because the outer solar system is brutally hard to observe. These objects are extremely dim, reflect very little sunlight, and move so slowly that tracking them reliably is difficult. Many may simply be undetected, or effectively untrackable with current surveys. In other words, what we call sednoids might just be the visible tip of something much larger. That raises a more serious question: if this pattern is real, what does it mean? Some researchers proposed a controversial idea: an outer structural zone beyond the Kuiper belt, where orbits are not random but shaped by a long-term gravitational influence we haven't identified yet. The mechanism, however, remains unconfirmed. And then things got even more interesting in the 2010s, especially after the Planet 9 hypothesis gained attention around 2016. Sednoid data was reanalyzed to test different models of the outer solar system. The result was messy. They don't clearly prove any single model, but they also don't reject all of them. It's as if every theory gets a small boost, but none of them gets a decisive victory. So the situation escalates. One anomaly can be coincidence. Multiple anomalies start to look like a signal. But there's a catch: the sample size is still tiny. There simply aren't enough confirmed sednoids to reach strong statistical confidence. That means you can see hints of a pattern, but you can't prove it's real. And so science ends up in a very familiar position: we might be seeing structure, but we're not sure it's actually there. Meanwhile, new discoveries keep coming in. Every new distant object slightly shifts the interpretation. Models get adjusted. Parameters get revised. Conclusions stay open. And Sedna sits at the beginning of that chain, almost like a reference point that everything else is measured against. It's no longer just an isolated object. It's a gateway into a possible outer structure of the solar system. And from that perspective, something unsettling appears. The boundary we draw in textbooks may not be a real boundary at all, but just the limit of what we've managed to observe so far. The Kuiper belt, once thought of as the edge, now looks more like a middle region. Beyond it, there may be structures we still don't understand, but right now, we can only infer them indirectly. Telescopes can detect light, but not the full architecture behind it. And when you put all of this together, a slightly uncomfortable picture emerges. We may be mapping the solar system using partial data, not the full system, which is exactly why Sedna becomes so important. Not just as a single object, but as a possible pointer, a clue toward something larger and still unseen, or maybe just a misleading outlier. And so the final question stays open, simple to ask, but incredibly hard to answer. Is Sedna just an isolated exception, or the first visible hint of a much bigger structure waiting to be understood? The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.